This is a lesson on gas laws. First thing we're going to talk about is pressure. Atmospheric pressure is due to the weight of the air above you pressing down on you. Pressure in general has an equation of force per unit area. In the metric system, force is in newtons or kilogram meters per second squared, area square meters. That's pretty cumbersome, so later on we're going to show you, well, I'll do it right now. There are different units of measurement of pressure, many more than what you should have. Standard pressure is the pressure of the air at sea level, and it is equal to, now these are all equivalent numbers, 1 atmosphere of pressure, 760 millimeters of mercury, which we'll get to later, which is 760 torr, named after the guy who came up with the idea of atmospheric pressure measuring it. The old SI unit, 101.3 kPa, Pascal, and kilopascal, so it's 101,300 pascals. That's the SI unit. The old SI unit. The new SI unit is 100 R. Kind of rounds it off to kPa, makes calculations a little bit easier. Well, what do you measure them with? Well, you measure pressure with either a manometer or a barometer. A barometer is open to the air, and it's mostly considered with air pressure. A manometer would be anything like pressure of a gas, like in a fire extinguisher tube, or how much pressure you have in your car tire. What you measure your car tire pressure with would be a manometer. A barometer is the thing that you use to measure atmospheric pressure. What you do is you have the weight of a substance, usually mercury, because it's liquid and heavy, dense. So the weight of the column of mercury pulling down is equal to the weight of the air pushing down. And they found out at sea level, the distance between the level of the mercury in the dish and the mercury level up here is 760 millimeters of mercury. 32 inches, something like that. But that's how they measured it originally, with open air mercury vapors and all that other good stuff, not used too often now. The reason they use mercury is at 760 millimeters. If you used water, it would be like 300, or it'd be 30 meters tall, which is the height of a 3-story building. So you'd have to have a 3-story building tall tube with water filled into it, not to mention water freezes. Okay, so that's the background on conversions. You use these standards to convert. Say we want to change 600 millimeters of mercury to kilopascals. This is the conversion thing, and we use the numbers up here to plug in. We want to get rid of the millimeters of mercury, and I ask for kilopascals. So 101.3 kilopascals from up here. Millimeters of mercury is 760. Do the math. Millimeters of mercury cancels dimensional analysis, and you get 80 kPa. So using any of these up here, you can convert from one to the other. The gas laws themselves There are many gas laws named after early scientists who discovered them. There are many of these laws. You don't need to know these, but samples are Boyle's. And you don't need to know these. I'll tell you when you need to know. Boyle's measured pressure and volume, and he said they were inversely proportional. If you increase the pressure, volume shrinks. Charles' law, he said that he measured the relationship between volume and temperature. Volume and temperature, they are directly proportional. If the temperature goes up, the volume goes up. Avogadro's law, volume and number of moles are directly proportional. This is like blowing air into a balloon. When you blow more air particles in it, the volume goes up. That's the relationship between volume and number of moles. And there's a Gay-Lussac law, and he did, pressure and temperature. You don't need to know those guys because you can combine them all together and you get the combined gas law. This is what you should know. This is what you should write down. P1 V1 over N1 T1, pressure times volume divided by the number of moles times the temperature in Kelvin equals P2 V2 N2 T2. So the first set of pressure, volume, moles, temperature is equal to the second set of those. Pressure and volume, the pressure P and the volume V can be in any units you want. N has to be in moles, and temperature must be in Kelvin. It has to be that way. There's no way around that. A couple of sample problems for this. If you have 300 milliliters of a gas at 40 kPa, and the pressure changes, that's original, the pressure is now 120 kPa, what is the new volume? Well, there's no moles and there's no temperatures, so you can ignore those. So it turns into P1 V1 equals P2 V2. Plug numbers in. The first pressure is 40. The first volume is 300 milliliters. It doesn't matter what the units are. The units will just carry over. The second pressure is 120. And the volume is what you're trying to find out. Do the math. Volume turns out to be 100 milliliters. Whatever the volume was over here will be the volume label over there. Another example. If you have 1 atmosphere and 1 atmosphere at 0 degrees Celsius, and the pressure is you change the pressure. Yeah. And the new pressure is 3 atmospheres, 3.0 atmospheres. What will be the new temperature? Again, plug them in. Pressure doesn't have to be anything. Temperature must be in Kelvin, so you got to add 273.1. So it's 1, so you have the pressure and you have the temperature. The volume and the number of moles can be just ignored, so it's 1, so pressure P1, T1, P2, T2. Plug in what you know. 1 atmosphere over 273.15 equals the new pressure, which is 3, over temperature. Do the math. 819.45, significant digits, 820 Kelvin. Temperature will always be in Kelvin on these problems. Another sample, you have 4 liters at 700 millimeters of mercury and negative 12 degrees Celsius. Find the volume at STP, standard temperature and pressure. The temperature must be in Kelvin, pressure matches up with what we have up here, and you use that from the list up above. Number of moles is changing, so it's going to be P1, V1, T1, P2, B2, T2. Plug in what you know. The first pressure is 700. The first volume is 4 over the temperature 261.15 equals 760 times the volume, which is what you're trying to find out. And 760 is coming from up here, standard pressure for millimeters of mercury, volume, and the temperature 0 degrees Celsius, 273.15 Kelvin. Do the math. 3.85 liters, and it's liters because you started off with liters. Last sample problem. Last sample problem for gas laws. You have 8 grams of oxygen at 100 degrees Celsius and 1.5 bar. And it has a volume of, and the volume is 40 cubic centimeters. How many grams of oxygen must be added to the container if the new conditions are 200 degrees Celsius, 4.5 bar, and a volume of 10 cubic centimeters? This one you need all 4 variables. P1, V1, N1, T1, P2, B2, N2, T2, because you have 4 numbers to plug in. The pressure is 1.5. The volume is 40. The number of moles is 0.25, so you got to change 8 grams of O2 times 1 over 32, the molar mass, and you get a fourth, or 0.25, and 373.15 equals the new pressure, 4.5 bar, the new volume, 10, and the number of moles, 473.15. Do the math, and you end up with 6.76 moles, but you don't want moles, you want grams. So 32 grams over 1 mole, and your answer is 216 grams of oxygen must be added to the container. The last thing for this set of problems is the ideal gas law. The combined gas law is used if you have two different conditions, 2 volumes, 2 liters, 2 temperatures. The ideal gas law you use if you have one set of conditions. What it does is it uses a constant of proportion, PV over NT equals some constant. In algebra they use K, math and chemistry we use R. Solve to get rid of the fraction. PV equals nRT. Notice there's only one pressure, one volume, one number of moles, one temperature. The constant R changes according to your units. It's probably easier just to memorize one value of R, and amazingly this R value shows up over and over and over again in different contexts later on in the second semester. So the R has a value of 0.8206. The units are important: liters, atmospheres over Kelvin moles. Kelvin and moles is not too problematic. That's what we've been doing before. But now the volume must be in liters and the pressure must be in atmospheres. If you don't have atmospheres, change it to atmospheres. If you don't have liters, change it to liters. So a sample problem for the ideal gas law: if you have 20 grams of oxygen at 200 degrees Celsius and 1,500 torr, what will be the volume? Well, you gotta plug things in. The atmospheres, so you gotta change torr to atmospheres. We did that up above. Torr, 1 atmosphere, 1 because it's coming from up here on the list. Torr is 760. Torr comes from Torricelli, which is the guy who hauled barometers all over the place measuring atmospheric pressure, so he was the one that did that. So it turns out to be 1.97 atmospheres, 20 grams of oxygen, molar mass 1 mole, 32 grams, turns out to be 0.625 moles, and the volume is in liters. The temperature, Kelvin to Celsius, so you add 273 to 200. Plug the numbers into PV equals nRT. Pressure, 1.97. Volume is what we're searching for. Number of moles, 625. Value of R, 8206. And the temperature, 473.15. Do the math. The volume turns out, the answer to B turns out to be 12.3 liters, because it's in liters. And that concludes, let's check. Yep, that concludes this lesson on gas laws.